with our presentation, P block element. This is a very short presentation which gives you a brief idea about P block elements. So let us have a glance over this periodic table. This is a modern form of periodic table, or when you see this modern periodic table, the elements lying onto the inferiority, that is from boron to neon, and from UUT to UUC, which is known today is as anorganium and organism. So from here, these 6 groups constitute the P block elements. So these are borderline elements which are typically non-metallic. These are not metals, however there are some metalloids exist in them also, but these are typical non-metallic elements, so we can't say them metals. They are basically non-metallic as well as metalloids. So P block elements generally belonging to group 13 to 18 of the periodic table are called P block. General electronic configurations of P block are Ns2np126 valence shell electronic configuration. They are also called as representative element or main group element, because S and P block elements are constitutively called the representative or main group element, in which there is one S group of elements, in which there is a P block of elements. Constitutively we call them as main group elements. So P block elements generally 13 to 18. These are the families of P block elements. These are the groups of periodic tables which constitute P block elements. 13th group is the boron family, 14th group is carbon family, 15th is nitrogen, 16th is oxygen, and 17th is fluorine, and 18th is the noble gas family, inert gas family. The elements marked in the pink color are typically non-metallic, whereas the element which are lighter in this diagram, these are typically metallic, and the element which are green, which are like nasty or dark green in color, are metalloids. They are known as semi-metals because their properties lies in between the metals and non-metals. They not truly resemble the metals, but they do not truly also resemble the non-metals. So we call them as in between metals or in between the non-metals, and the specific name which is designated as metalloids. Introduction of, so specifically we'll talk about group 16. So members of this family are oxygen, sulfur, selenium, tellurium, polonium. Physical properties of the group 16 are electronic configuration. Its electronic configuration, which is Ns2np4. So here is the electronic configuration of the respective elements. Atomic sizes generally increases down the group every time a new shell is added as we move down. This is actually true because when we move down the group, there is the addition of new shells each time. So with the addition of new shells, the electrons or the distance of the center of nucleus and the distance of the outermost shell increases gradually. So atomic sizes also increases gradually. But if we compare the size of group 16 element with group 15, then we see that group 16 is smaller due to the increased nuclear charge. Then we compare ionization energy. Now ionization energy, if we compare ionization energy, this has two gradations. First is down the group and second is across a family. So when we move down the group, there is a decrease in ionization energy, and when we move across a family, there is a gradual increment in the ionization energy of all the elements because due to the increased effective nuclear charge. Fourth is the electronegativity. Group 16 elements are also electronegative elements than group 15 element because of small size and high effective nuclear charge. This group has second highest electronegativity in whole of the periodic table. Oxygen is second most electronegative in the periodic table after fluorine. Down the group, electronegativity decreases as size increases. Oxidation states, they generally show -2 oxidation state. For oxygen, common oxidation state is -2, but oxygen also shows +2 oxidation state. This is an anomaly of oxygen. This is not normal. This is anomaly of oxygen. In the case of OF2 and in the case of O2F2, the oxidation states actually in the case of oxygen are positive. We can't expect by an electronegative element to show positive oxidation states, but in the case of oxygens, it is true. In these two specific compounds, which are most important, which are not its most important compounds, but we study them. One compound is oxygen difluoride, and second compound is oxygen fluoride. The oxidation state here in both two are respectively +2 and +1. Oxidation state of oxygen is in positive because oxygen is less electronegative than fluorine. So this is anomalous behavior of oxygen, but only with the most electronegative element, that is fluorine. For sulfur, the oxidation state is +2, +4, +6. Because of vacant D, like in SO2, the oxidation state of sulfur is +4, and in sulfuric acid the oxidation state is +6, and in H2S it is -2. Down the group the vacant d orbitals are present, therefore they all can show +2, +4, +6 states. So what are the anomalous properties of oxygen? Oxygen, or in fact every element of the respective family, every first element of the respective family, I should say, is anomalous, is not at all typical in its behavior when we compare it with all the elements present in that particular family. The main reasons are somewhat similar, as we will see from oxygen. You can also compare it with all the other first members of respective families. It has small size in its family. Second, it has highest vacant energy, it has highest ionization energy. Second, it has no vacant orbitals present in it. Second, it is highly electronegative in its family. So these are basically its anomalous properties. Then, electron gain enthalpy. A long period, it is more electronegative because of attraction towards electron because of increased nuclear charge. Down the group, electron gain enthalpy keeps on becoming less negative because nuclear charge decreases and size increases. The trend that was expected, this is oxygen, selenium, then selenium, tellurium. This is actually wrong trend, but right trend somewhat atypical. That is, oxygen has low, sulfur is highest, then selenium, and then tellurium is lowest electron gain enthalpy. Oxygen has less electron gain enthalpy than sulfur. Why? Because due to the small size of oxygen, the incoming electron suffers more repulsion. Therefore, electron enthalpy is less negative as compared to sulfur. This whole group is called chalcogens. The oxygen family is also known as chalcogen, or they are known as ore forming element, because aluminium is typical in forming bauxite ore, lead is typical in galena, mercury is in cinnabar, and zinc in zinc blende, and sphalerite. And there are many more ores of these typical these 6 or 7 elements in the group, in the period 6, group 6. Elemental state of oxygen and sulfur. Oxygen exists as basically a diatomic gas, whereas sulfur dioxide exists. Sulfur exists in acid form, is called puckered ring form, as shown. In case of oxygen, p-pi bonding takes place, but in sulfur no such bonding takes place. That is the reason why oxygen exists as a gas and sulfur exists as a solid. Chemical properties. So when we see the order of reactivity is expected, oxygen, then sulfur, then selenium, and tellurium. That is why oxygen is quite reactive, and as we move down the group, reactivity decreases. Oxygen in this case, in this group, is quite reactive as the bond between oxygen atoms is quite strong, and the energy required to break is 493.3 kJ per mole. Almost all the reactions of oxygen are exothermic. Therefore, the reactions are called combustion reactions, or the oxidation reactions of oxygen. The most stable compound of this group are selenides. Selenides are basically compound of selenium, and tellurides are basically the compound of tellurium. These are most stable compounds because they have diffused size of atoms. They they have dense. When these form compound, they are very strong and have very high energies, or very high bond dissociation energies. So they form most stable compounds. So this was all about this presentation. Thank you so much.